Good morning. So today I will discuss to you the concept of limits, particularly the intuitive concept of limits. Now, limits is a fundamental concept in calculus. In fact, we need to understand limits for us to appreciate and also to understand the concept of differentiation. Okay, so consider this function f of x equals x squared, and we shall define this function on the interval 0 to 2. Okay, and say we label our integral as, our interval as, say this interval is I sub 1, which is a closed interval from 0 to positive 2. Note that this function is increasing. This function is strictly increasing on this interval from 0 to positive 2. Now, I'll introduce to you the concept of nested intervals. What is this nested? Two intervals, say interval I sub 1 and say interval I sub 2. These two intervals are said to be nested if one interval is a proper subset of the other interval. In symbol, say I sub 1 is a proper subset of I sub 2, or we can say I sub 2 is a proper subset of I sub 1. Okay? So, we have this interval from a closed interval from 0 to 2. Now, let I sub 2 and I sub 1 be nested intervals. Okay? So, center at A equals 1. So this is our A equals 1. And so we will introduce a nested interval. Say from 0.5 to 1.5. And say we label this as I sub 2. Therefore, I sub 2 and I sub 1 are nested intervals because I sub 2 is a proper subset of I sub 1. When you say proper subset, all the elements of the interval I sub 2 are elements of the interval I sub 1. Okay? And if we are to introduce another interval, say, we all know that this is A equals 1. Another nested interval center at A equals 1. So say this is I sub 3. So I sub 3 and I sub 2 and I sub 1 are nested intervals. Okay? Now, the graph of f on this in these nested intervals. So we have our notation for nested intervals. I sub 3 is a proper subset of I sub 2, which is a proper subset of I sub 1. Or we can write this in this manner. I sub 1 is a power set of I sub 2, which is a power set of I sub 3. So these are nested intervals. Now the graph of f, the graph of f on these three nested intervals can be enclosed by the rectangles. Diba? Say for example, let's have this I sub 1, this interval I sub 1. So it's an interval, a closed interval from 0 to 2. So if we are to evaluate 0, if we are to evaluate our function at point 0, the value is 0. If we are to evaluate the function at point 2, the value is 4. Meaning to say, okay, so we can enclose the graph of f on the with say R sub 1, meaning region 1. So this region 1 enclose the graph of the function at this interval I sub 1. How about if we take the interval I sub 2? Okay, I sub 2, it's since we use closed intervals, so this is included in the set. Okay, so this is the infimum in real analysis. The infimum of I sub 2, okay, the infimum of I sub 2 corresponds to this value in the value of the function. Okay, so this, okay, and for the in real analysis we call this as the supremum. The supremum of interval I sub 2, this one. This is supremum, kumbaga in layman's term, ito yung pinaka greatest value in the interval. Okay, and we can enclose this with this by this rectangle. Okay, so we label this as R sub 2 or region 2. So R sub 2 enclose the graph of the function at interval I sub 2. Same manner, for interval I sub 3, the infimum corresponds to this f of x, and its supremum corresponds to this, so we can create a rectangle. So we label this as R sub 3, R sub 3. Now if we are to continue, if we are to continue this, say if we are to use the interval I sub 4, such that it's a nested interval, if we use I sub 5, I sub 6, that means up to infinity, the height of our rectangle decreases, right? Papansin nyo na nagdi-decrease siya. Okay. As values of x, kumbaga, as values of x approaches a, diba our a here is yung 1, okay? And these intervals contains values of x surrounding point a, okay? As x approaches a from either from left or from right, what happened to our f of x? What happened to the function value in this set of x's? In this example, as values of x approaches a, the function value approaches 1, right? Nag-a-approach siya dito. Okay. Papaliit ng paliit yung rectangle natin to the point na its limit is 1. Therefore, as x approaches a, the function value at x approaches 1. Or we can write this as the limit of the function f of x as x approaches point A is 1. Now let us consider this example. Find the limit of the function y equals, or y, a function of x, which is equal to 3x minus 9 over x minus 3, as x tends to a equals 3 using nested rectangles. Okay. So this is a rational function, therefore we have to determine its domain. Okay. So what's the domain? What is the domain of this function? So the domain of this function, say function f of x, is the set of all real numbers except 3, right? Because 3 is not included in the domain, because x equals 3 will make the function undefined, or will make the function not real and not defined. Note that this function y, a function of x, which is equal to 3x minus 9 over x minus 3, say the limit of this function f of x as x tends to a equals 3, or as x approaches 3, is equal to 3. How did we get 3? Therefore, the limit of the function of this function as x approaches 3 is equal to 3. But how did we get 3? Remember that we cannot evaluate this function at x equals 3, because this 3 will make the function undefined. And so we have to transform this function. So there is a need to transform. So we transform this function, say its transformation becomes g of x. To transform this, we have, we factor out 3, then we have x minus 3 over x minus 3. Okay? Then is equals to 1, and so g of x is equal to 3. So this is a transformation, g of x is a transformation of the function f of x. What does it mean by transformation? It means f of x behaves like g of x, except at x equals 3. So the graph of f of x is the horizontal line y equals 3. So if we sketch the graph, so the graph of f of x is the horizontal line. It's a horizontal line that corresponds to y equals 3. However, there is a hole at x equals 3. Say this is x equals 3. Therefore, merong hole dito, or merong butas. Bakit meron tayong butas dito? This corresponds to x equals 3. You need to say that, based on our domain, the domain is the set of all real numbers, right? Except 3. Okay, because 3 will make this undefined. Now, As we consider smaller and smaller nested intervals centered at a equals 3. Okay. Ano yung nested intervals nga? So say we have this I sub 1. So yung I sub 1, ito yung kung mag-nest, ito yung nested interval. I mean, ito yung interval I sub 1 natin. And then, ano yung possible na rectangles natin or in closed rectangles. No, rectangles kasi closed naman ang mga rectangles, right? So, the height of the rectangles can be made arbitrarily shorter than the preceding rectangle since the graph is a flat line. So, arbitrary So, sabihin natin, ito yung rectangle niya. Okay? But the height is arbitrary, kumbaga, as shorter as you can imagine. Now, if we consider another interval, say I sub 2, such that I sub 2 is a nested interval with respect to I sub 1. So, ito naman yung corresponding rectangle niya. Okay? Say another nested interval I sub 3 such that I sub 3 is a proper subset of I sub 2 and I sub 2 is a proper subset of I sub 1. Or in general, nested intervals. So, kung napapansin natin, as x, okay, ito na lang. As x approaches 3, function approaches 3. Diba? Ga-approach siya sa 3. Ito yung, kumbaga, ito yung limit niya. Okay? In other words, these rectangles cluster about the point 3, 3. So, take note ng term cluster about point 3, 3. Now, let's have example number 2. Find the limit of the function y, a function of x, which is equal to 1 over the quantity x minus 2 square as x tends to a equals 2 using nested rectangles. So, the graph of this function has a vertical asymptote at x equals 2. Diba? Because the domain of our function f of x is the set of all real numbers except positive 2, right? Hindi pwedeng ma-take ng function na to yung x equals 2 kasi magiging undefined siya or not real siya. So, kung mag-sketch tayo ng graph niya, okay. So, this corresponds to x equals 2 and this is the vertical asymptote of the function. And the sketch of its graph looks like this. Oh, sorry for that. The graph has to be symmetric. Okay. Well, let's just assume that my graph is symmetric. Okay, so this is the sketch of the graph of this function with vertical asymptote x equals 2. Okay, now if we are to use the concept of nested intervals or nested rectangles, say we take this as our I sub 1. So, tama. I sub 1 or say Say, take this as our I sub 2. Say, this is I sub 3 up to infinity. Ano? Now, what happened to our rectangles? For any interval I centered at a equals 2, the graph of this function f cannot be bounded by a rectangle. Diba? Kasi sabihin natin yung pinaka-small na interval. Okay? And then we sketch its rectangle. Hindi siya bounded. Paano hindi bounded? Remember that this graph extends to infinity. And so, it's not bounded. The graph of f cannot be bounded. Pag sinabi natin bounded, naku-close siya, kumbaga, yung concept ng rectangle, naku-close natin siya. But in this case, hindi natin ma-determine yung height ng rectangle. Why? Kasi it extends to infinity. So, it's not bounded. Therefore, the limit of our function f of x as x approaches a equals 2 is, or say, ito na lang, d and e, or the limit does not exist. Okay? The limit of this function as x approaches 2 does not exist. Why? Why does not exist? Because we cannot bound. The graph of f cannot be bounded by nested rectangles. So take away, the limit exists. The limit of the function exists if for all nested intervals, the heights of the rectangles decrease. Okay? Kumbaga, as x approaches this point, the height of the nested rectangle must decrease. Yung concept natin na cluster. Dapat magka-cluster ang mga nested rectangles natin. But in this case, hindi siya nagka-cluster. Why? Kasi hindi nagdi-decrease yung height ng rectangle natin. In fact, it increases infinitely, di ba? As x approaches this a equals 2, the height of the rectangle increases infinitely. So, hindi siya nagka-cluster. Therefore, the limit do not exist.